Okay, for question 3 on paper 2, it's a fairly straightforward probability question. And it says the probability that a certain rugby player scores from each place kick he takes is a 85% or 0.85. So he can either only score or miss, and that's what makes this a Bernoulli trial, if you like. Now, I'm not going to use any formulas that you may have learned in Bernoulli trial. I'm kind of just going to work this out using my own kind of method, which I think is kind of straightforward, and you don't need to remember any formulas with difficult notation. So if we know the probability he scores is 0.85, well, that would imply then that the probability he'd miss is 0.15 or 15%. So what about this? He scores in exactly 3 of 5 attempts. Now, if we think about the 5 attempts he takes, we can go like this. So we'll draw a box for each one, and here's each attempt, we'll say, right? So I always use this method, even for very complex probability problems. So let's write down one scenario where he scores exactly 3 times. Let's just say it's this. He scores the first, he scores the second, and he scores the third. And then, therefore, if he only scores 3 times, he must go miss and miss in the 4th and 5th attempt. Now, it's pretty straightforward for us to get this probability answer for this one. So we can say each score is 0.85. So each of these is 0.85. And therefore, each miss is 0.15. So if we look at this, so we have 3 0.85, so that's 0.85 cubed, because these are all multiplied. And if you're unsure of what the difference between multiplying and addition here is, well, this is one scenario where he has to score the first and the second and the third and miss the 4th and miss the 5th. And by saying and, we're effectively saying multiply. If we wanted to do add, we'd have to say or, but that's not the scenario here. We don't want him to score the first or the second. He has to go this way. So that's 0.85 3 times multiplied, and then multiplied by 0.15 twice. So if we do that on our calculator, let's see what we get. So we get 0.85 to be cubed, multiply that by 0.15 to be squared, and that gives us this number here, like 0.13. Let's just go 2 or so, right? So that's roughly what we have for that. But that's only one scenario. How many scenarios are there? Well, we could come up with a couple of scenarios, but of course we're not expected to do that. But I'm explained this way because here's another scenario. Score, miss, score, miss, and score. This is another perfectly acceptable scenario, which of course again is going to have 3 0.85s and 2 0.15s. So it's going to give us the same number again. So this will definitely work out the same as this one, just in a different order. But we need to know how many of these are there. Why do we need to know that? Well, because if this is one scenario here, I think it's actually 1382. If this is one scenario, here's another scenario. Well, it can be this way, or it can be this way, or it can be some other way. So literally by saying the word or, this is one scenario. So or this scenario, so we'd add this probability, or some other scenario, so on. So how many scenarios are there? Well, we use the choose notation here. We have 5 boxes. We want to arrange either 3 scores or 2 misses. And it doesn't matter which one you pick. So let's just say we want to rearrange 3 scores. How many different ways can I arrange these 3 scores? So you can see I arranged them so the first, second and third was a score. Then I arranged them so the first, third and fifth was a score. So how many arrangements of these 3 scores can I make in 5 boxes? Well, that's simply the notation 5 choose 3 for an arrangement. Now actually I also said you can do arrange the misses, because 5 choose 3 is the same as 5 choose 2, and that's something you're expected to know. So this is how many ways there are 5 choose 3. So let's get 5 choose 3. So 5 shift and this button with NCR on top here, choose 3, and that gives us 10. So there's 10 different ways. So essentially I'll have 10 of these answers, which I'll all have to add up. And of course 10 times this is going to give me the same answer. So 10 multiplied by 0.01382. And if we do that, multiply that by 0.01382, it wants 4 decimal places. So that gives me 0.1382. I just literally brought it all up by multiplying by 10. And so that's it. And 4 decimal places, that's a good enough answer for us here. So that's the first part. So the next part then says, what about this? He scores for the third time on his fifth attempt. You see this question so many times. Really try and understand this. I'm going to use the exact same method as I used in the first part. So again, let's draw out the 5 boxes here. Let's work out one scenario. So here's my 5 boxes. So he scores for the third time on his fifth attempt. That means on his fifth kick, that's definitely a score. So that's definitely an S. So we can't change that. But what about these 4 goals preceding it, right? Well, if that's his third score, he must have scored twice before that to give him a scenario like this. So again, this is an acceptable scenario where he goes score, score, miss, miss, and score. So of course this is a 0.85, this is a 0.85, this is a 0.15, a 0.15, and a 0.85. So this is one scenario that works out the same as the first actual scenario where he scored 3 times, because it's still the same way, but it needs to be in a particular order now. There's only so many acceptable orders. In the first part of the question I did 5 choose 3 to see how many ways he could score 3 times, but that's not acceptable anymore because there's only so many ways he can score 3 times where his final score is on his final attempt. So for instance, in the first part of the question, this would not be an acceptable scenario for this question because his final score was on his third attempt, his fifth attempt was a miss, and we need his fifth attempt to be a score. So how many ways can we do this so his third score is on the fifth attempt? So this is one way, and it works out the same as the first scenario we worked out in the first one. So this is roughly cutting down decimal places, 0, 1, and 3, 8, 2. Okay, so how many ways are we going to do? How many other ways do we have here? Well, we also could say score, miss, score, miss. We could do that, and that'd be 2 scores, 2 misses, and of course his last one has to be a score. So really what we're arranging these 2 previous scores within these 4 boxes in the front. So we want to arrange 2 things in 4 boxes. That's 4 choose 2. So let's do 4 choose 2 in the calculator. That's 4 shift this NCR button and 2. That means there's going to be 6 arrangements that we can have. So literally we have this 6 times. So our answer is going to be simply 6 multiplied by 0.138. So that's 6 times this, which is actually 0.08292. Not this. So 0.82, and it says 4 decimal places, so I don't need this 2, so just 0.0829 is our answer here. That's 6 times this number here. So the final part of A says he scores at least 3 times. So let's think about that. He has to score at least 3 times. So that means he can score 3 times and he can miss twice. He can also score 4 times and miss once, and he can also score all 5 times. These are all the acceptable scenarios where he scores at least 3 times. He scores 3 times, 4 times, or 5 times. We actually have the answer for this from the first part. The probability that he scored 3 times was 0.1382. Now what about the probability that he scores 5 times? That's actually pretty easy because there's no arrangements going on here. He has to score every time. That is simply 0.85 for the probability to score 5 times. And it doesn't matter what way you arrange them, they're always going to be the same. So there are no choose notation here. So let's get that. A 0.85 to the power of 5. And that gives us, I'm going to stick to 4 decimal places, 0.4437. So I have this way and I have this way, but what about this way in the middle? The probability he scores 4 times, I need that. Well, let's think about that. That's going to be 0.85 4 times for the 4 scores, multiplied by 1 miss, which is 0.15. So, how many combinations are there of 4 scores and 1 miss? So, let's think we have 5 boxes, again, and we're arranging 4 scores, or 1 miss. So 5 boxes arranging 4 scores, that's going to be a 5 choose 4, which is the same as 5 choose 1, because for arranging 1 miss is like arranging 4 scores. So we have this 0.85 for the 4 scores and 0.15 for the miss, and we know it's going to be 5 choose 4 amounts of those if you want combinations. So let's get this here first. So let's do 0.85 to the power of 4 equals, and then multiply that by 0.15, and we get 0.0783. Okay, so let's write that, 0.0783. How many of these am I going to have? Well, I'm going to have 5 choose 4 of them. So 5 choose 4 gives us 5 of those. So let's multiply that by 5. And we get a 0.3915. Okay, so the probability he scores 3 times, we had from the first part, was 0.1382. The probability he scores 4 times, now we just had to work out, is 0.3915. And the probability he scores all the time for all 5 kicks is 0.44. So he has this way, or this way, or this way. So we can add all those together, plus 0.4437 plus 0.1382, and that gives us a total of 0.9734, which is our answer for that part. So we're on to the last part of question 3, and I love these questions because they are straightforward, and they can be daunting because of all these symbols, but there's only normally only 1 or 2 rules you have to stick to, and the numbers are usually really straightforward. So we're told that A, B, and C are these 3 events, and this is what we're given. We're given the probability of A, we're given the probability of C, we're given the probability of A intersection B, and the probability of B union C. And also says that A and B are independent. So I put that in a red box. And also says to find the probability of B intersection C. Now, the first thing to look for here is this. The individual probabilities. We have A, we have C, we don't have B. But we're told that A and B are independent events. It's our first big clue. If A and B are independent events, that would imply that the probability of A intersection B is equal to the probability of A multiplied by the probability of B. So why would we look for that? Well, because usually we kind of need the individual probabilities to find out. So it's our first go-to here. And I'm not going to get too much into this. I'll make a video on this specific topic about the rules of conditional probability that are needed. But let's just tackle this particular question and see, can we get the probability of B that we're missing here? So the independence gives it to us. Since they're independent of each other, it doesn't matter which happens first. So that's why multiplication being commutative, probability of A multiplied by B is the same as the 2 of them happening together. So let's look and see what we have. Do we have the probability of A intersection B? Yes, we have. It's a half. Do we have the probability of A? Yes, it's a third. A third multiplied by the probability of B is now going to be, this equation must be true because they're independent. So if this is true, what can we actually do? So actually, sorry, I made one mistake. I just checked the question there. This is actually a 12th. Sorry about that. So the probability of A intersection B is 1 over 12. So what we have to do here to get rid of this, essentially we have to multiply, say, across everything by 3 to get rid of this third, to get this stuff on its own. So multiplying everything by 3 will give us 3 over 12 here. 3 times a third will cancel, giving 1, leaving us with probability of B. So if you like, that's what I did here, just to get rid of that third there. And I get 3 over 12 is equal to the probability of B, which is now 1 over 4. Okay? So we know 1 over 4 is equal to the probability of B. Now we're actually looking for the probability of B intersection C. Can we make a new rule that includes the probability of B intersection C? In this case we can. We can get the probability of B union C. Now that's using the other part here, given that we don't know. What do we know about B union C? Well, we know that the total set probabilities for B union C would be the probability of B plus the probability of C. And of course, when we have that, we have to subtract the intersection because we can't include it twice. Again, these are in your rules. This is a rule you kind of have to know, right? So here's a rule. The probability, and actually what you may have learned in your book is something like this, is the probability of A union B is equal to the probability of A plus the probability of B minus the intersection, because actually when you delve into this you have to subtract intersection, because by doing probability of A, that includes the intersection A and B, and then the probability of B also includes the intersection, which is fine to use, but you've actually included it twice using these. And the same rule goes for here with B's and C's. So the probability of B union C is equal to the probability of B plus the probability of C minus probability of one of those intersections. So we actually have a figure for B union C that's 5/8 given to us in the question. So that means 5/8 is now going to be equal to the probability of B, well, we found that out there in the first part, was a quarter. The probability of C, which was given to us as a half, and now minus the intersection, the probability of B and intersection C, well, that's something we're looking for, so we don't know. So let's just leave that, we'll say here, as, we'll just call it what it is. So 5/8, and just a small bit of maths here now, so what's that, 2/8, and that's going to be 4/8. So I have 5/8 equals to a 6/8 here, and minus this stuff here. So a small bit of rearranging, that's going to be 5/8. Now that's 6/8, so we'll bring that across, going to be minus 6/8. It's going to be equal to minus this stuff here. And of course that's minus 1/8 is equal to minus this stuff. And of course we're going to change now, aren't we, the signs to give us 1/8 is equal to the probability of B intersection C. So we have that, and now the last part it asks us, investigate whether they are mutually exclusive or not. So let's save a little bit of paper, let's see, can we do that here at the end? Well, mutual exclusivity tells us for B and C, if they're mutually exclusive, well then the probability of B intersection C should be equal to 0. So that's a condition for our mutual exclusivity here. And we've actually just got an answer for that. So this must be true as mutually exclusive. So it's not. So if they're mutually exclusive, that means they don't affect one another. But they must affect one another because there's an intersection point where both of them can happen together at the same time. So a probability of B intersection C must be 0 to be exclusive events. But so no, they're not mutually exclusive because we actually have a value for B intersection C. So we can definitely say that B and C are definitely, so we can say probably B and C, both these events are not, and you will have to say this in your answer to get full marks, are not mutually exclusive. Like sometimes you do need to require that little English sentence or language at the end, it's not just all numbers. And that's question 3 done.